Thank you guys for coming to this talk. Is it after lunch or have you had lunch yet? I usually get the after lunch slot, which is terrible, so yay. I'm quite excited to talk about this thing right here. Basically what I'm doing is the talk is all demo. It's all a notebook. There's no slides. I'll just walk you through a code example of building a predictor for taxi fares. And the data set I use is New York City taxi fares. And I've been doing this talk for, like a year now or so. But this is the first time I've done this in New York. And I actually took a taxi to get here. And I predicted my fare. And it wasn't right. But I was super excited this morning. When I took the taxi, I was like, yeah, let's do this. And as the meter rose above the predicted fare, I was like, yeah, this is not so great. But anyway, the presentation has two people on it. So there's Stuart Bryson, who isn't here, but he built this thing together with me. And my name is Bjoern. I work for a company called Pythian, and I live in Ottawa, so just like an hour flight north of here. Like I said, this whole thing is, there's one more interesting thing. You can see that I'm using not Oracle's cloud, I'm using someone else's cloud. The reason for that is, where is it? Where has it gone? I was here. If you look for Oracle Data Science Cloud Service, which is the same thing basically that I'm showing today, is you can see that is coming soon. So this should be a bit of a preview of what I think Oracle launches. I haven't talked to the product team, but from what I understand is they bought a company called datascience.com. They are really strong in managing notebooks and collaboration for machine learning. So we'll have a look at what a notebook is. We'll have a look at TensorFlow, which is an open source framework for building machine learning models. And then I'll basically walk you through how we can build and train a model and then run predictions on top of that. So if you see someone else's cloud here, that's why. It's just because Oracle's product is not available yet. Like I said, this is all a notebook, and if you've never heard of what a notebook is, it's basically a web server that exposes Python to you, and you can basically write Python code and markup language in what's called a notebook. The notebook is all code, so you can check this into Git. Actually, the whole presentation is on GitHub, so you can check it out. You can run it yourself. But since it's actually code and markup, I actually have to run some code. So the first thing I did is I just imported some of the packages that I'll be using later. And then here's some markup about what I want to do. So what I'm doing here is I'm showing how we can train a machine learning model to make predictions based on what's called a feature, on certain parameters. Like if we know certain input things, then the traditional way of doing it would be if we have inputs and we have some rules or some algorithms that we can develop to come up with a prediction of the output. That is how we typically write things, and the thing that we write and the thing that we have to develop is called an algorithm. Machine learning follows a slightly different approach. You still have a black box. It's just not called an algorithm. It's called a machine learning model. And instead of feeding it rules, we feed it data, let it train by itself, but the overall thing it does is still the same. I give it some input, which is the things that I know, to receive an output, which is the thing that I want to know about. So why am I using this example for taxi fares? The main reason is that New York's been awesome about publishing this data. So there's a data set about 150 million rides per year for the last 10 years. And you get the drop-off point, the pick-off point, you get the duration, you get the fare, you get the passenger count, lots of interesting things that you can then use to actually do stuff on this. Also, if you've done anything in machine learning, there's this website called Kaggle. They usually have challenges challenges with tournaments about use this data set to find out something. And this taxi fare set is one of the data sets that comes up a lot. So it was easy for me to find that and to take other people's models and other people's stuff and just improve slightly on it. So if you look at New York City taxi fares, you would think it's actually easy enough. Because there are certain rules, right? There's an initial charge, and then there's a charge per minute or per mile, and then there's surcharges. And one of the things that I just found out today was there was an increase, so that sucks. There's two things that sucks. Well, it's I have to pay more, but also all of my training is now pretty obsolete because I trained it on last year's fares and the last 5 years' fares, and now the fare rule structure is different. So naturally, the same ride will be more expensive. So. That's a bit of a problem. But also, some of these things are hard to calculate. Like before I get here, it's hard to know how long will the ride be, how long in terms of time, but also long in terms of kilometers or miles. So if I just want to get from A to B, it's actually hard. And it depends on the time of day, obviously, and which route you take. And here I just took what's this, LaGuardia to here. Different routes you can take, different length, different times. And we might not know this beforehand. So that's kind of why I want to do this. So let's have a quick look at the data set. This is already available on BigQuery, so that it didn't have to import anything. So I just write a query and select a few fields from it. And then here is me displaying 10 records from this data set. And we can see that it should contain the date time of pickup. So 2009, 10 years ago, someone got picked up here, dropped off there. It was one passenger. And we can see there are some things that look a bit fishy. So trip distance, 0 miles. That sounds a bit fishy. Total amount, 0. Sounds a bit fishy. And the fare amount is just the minimum. That might be a bit fishy. But we can see that's the kind of data we have. So you have pickup, drop-offs. We have the time. We have the distance. And then we have the fare amounts. So there's different things we can do with this data set. One obviously is reporting, like good old style reporting, where you might want to say, give me the total amount of rides for a given month, or the average length of a taxi ride, all these things. And then you get into more fancy things where you do analytics and explore the data, and you might be interested to see which times of the day are the most lucrative for taxi drivers to ride. Or you could do what we are doing, which is predictive analytics, which is at the high level, like how much money am I going to make next month riding a taxi? Or and then the question that I want to ask is, if I want to get from A to B, what is it going to cost me? That's a simple question that I wanted to answer. So let's just try to plot some of the data. This is plotting the distance, the fare amount over the distance. And we would expect, like, the longer the ride, the more expensive the fare. We can kind of see that, but we also see there's some other weird stuff going on. There's these rides that are super expensive but have 0 miles. That's a bit odd. And then there's a few outliers here as well. So let's filter this out and just say, let's filter on those. Trip distance should be greater than 0, obviously, and the fare amount should be greater than 250, because that's the absolute minimum. And then it looks like this. So we can see there's a few rides over here that are getting very expensive but don't go very far. And then we can see there's a lot of linear correlation here. And then there's 2 straight lines. Everywhere else where I did this talk, I asked, like, what is this? You probably know this, right? Right? Right. Yeah, it's JFK. It's a flat rate from JFK. Does LaGuardia actually have a flat rate? It doesn't, right? So I think it's got to be JFK. But I think the 2 lines are either for a price increase, or it's because sometimes there's a surcharge for the rush hour or the after hours or something like that. But that's interesting enough, because if this was just linear, then machine learning things would actually have a quite easy time to pick this up. But there's these odd outliers where it will, like any model we train, will have to learn that these things exist and that they have this flat rate. So let's see how that works. The other thing I wanted to know is, like, is the toll included in the total amount? Because there was one field that's called the total amount, and then there's one that's called the fare amount, and one that's called the tolls amount. And we can see that the total amount is sometimes more than the sum of these two. And the reason is, if you pay with credit card, then the tip is included in the total amount. If you pay cash, then the total amount is just the fare amount plus the tolls amount, which tells me that for everything that I do, I have to look at the sum of tolls plus fare and not have a look at the total amount, because that has tips in them, and I don't want to predict the tipping amount. If I look at my data set here, this is just basically the profiling of the data set. I can see this small subset has 11,000 rides in it. And I can see the min and max for all these values. And if I look at this does not look like a good longitude, and this is not a good latitude. And there's a few things that are just outliers here. So I want to do some quality control, and I want to filter the data, because there's no way this is a valid GPS coordinate in New York, and there's some other things. I think the trip distance, 30 miles might actually still make sense. So let's add some more filters to our SQL. So we say longitude, latitude should be between these, and passenger count should be above 0, because if you have 0 passengers, then you really shouldn't be charging for the ride, unless you're laundering money or something. So now that we've done this, we would still hope to have like 10,000, 11,000 records maybe to work with. Let's see. It's always awkward when it's just running like that and there's nothing for me to say or do. This is getting really awkward. Let me just go ahead. So any model or anything that we do, we'll have to kind of get a feel of how good is this model, how good is this thing that I built, oh, there it is. So it's still 10,000 records or 100,000 records even. So how do I score the accuracy of a model? One way to do it, and there's several ways to do it. The one that I chose to do is the mean squared error or the root mean squared error. So basically what I do is I take a validation data set and I get the actual fare that it took. I take the fare that was predicted. I take the error between them, I square them, and then I sum them up, get the mean, and then I take the root of all of that, because that will be the same unit basically that I had. And the reason for using this as a measure is it'll penalize the higher deviations more than lower ones. So if I have one prediction that's $2 off versus two that are $1 off, I want to penalize the $2 prediction more than the others. So I use this formula, the RMSE, throughout this thing. And some of my later examples don't have the root squared, so you just see the squared value of that. First thing I do is I create data sets. So I just create local CSV files, and all the training is basically happening locally in this machine that's running this data, the notebook for me. And there's a training data set, there's a validation data set, 100,000 records in total. I write them out to CSV. Actually, I've already done that. And I can look at the headers, like this is like what the file would look like. So it's a CSV file with a bunch of writes in it. So before we get into machine learning, the first thing I want to do is just, as a benchmark and as a rule of thumb, just get the Euclidean distance, the distance as the crow would fly, which obviously isn't perfect because there's bridges in New York and you can't just go direct, but it's the easiest thing for me to calculate. So let's calculate the average trip distance and the average trip price and get basically the dollars per kilometer or the dollars per mile as the crow flies, like just the distance. And for that, there's also one more point to make, is we had the distance driven in the data set, but I can't use this later on because I will not know the distance driven when I want to make predictions. So I can only look at the values, obviously, for all of the stuff that I'm doing now that I know from the start. I know where I am, I know where I want to go, and I know what time of day it is right now at the pickup. I don't know how long the trip will be in terms of miles or time. So this is a little program here, so it calculates that. You can see it here somewhere. I take the mean fare amount divided by the mean distance, and this will give me the dollars. So it says 255, 256 per kilometer, and the error is $8.80. So that just means that whatever it predicts, it's off by kind of $8 usually. That's just a benchmark, right? So when we do machine learning, we obviously want to get better than that. So let's see if we can get better than $8 or $9. Everything I do uses TensorFlow. And TensorFlow is an open source library that has a bunch of machine learning stuff built into it. And there's people usually use Python to interact with it. And the first thing I want to do is I want to use a very simple algorithm called linear regression. If you go back to like high school math, you read all your linear equations. It's the y equals a times x plus b times x plus c times x. So if we have all of our input parameters, all the x's, and then we just need to find the proper weights for each to come up with the linear equation. So if we could fit basically the taxi prediction into a linear equation like that, that would be super simple and we can easily train this. So the way I do this is I specify the columns I have and I say my features are basically all my columns except for the fare amount. That's the very first field. That's called a label. So the label is the thing you want to predict. Features are the things that you know. And I say there's a training data set, there's a validation data set, and this is my function. I basically just say take all the values as they are and train this. So this is me making the columns, and this is me actually running the training. This will take like a minute maybe. You can see the log output. And doesn't take very long. This is quite simple. This is also something that databases have built in. So if you've ever looked at Oracle databases and the kind of machine learning you can do within Oracle itself, linear regression is one of these easy algorithms that you can easily run within the database like itself. It's because it's quite easy to train, quite easy to implement. All right, so that's done now. So now comes the time where we want to validate it. So let's see what the RMSE is. And the RMSE is 9.2. So this is worse than our benchmark. So that sucks. We're not done yet. So we will have to do a little bit more, right? So linear regression, easy, good, but not good enough for our case. The total cost, the fare amount, which is the fare amount plus the tolls amount. That's the label I want to predict. So if linear regression isn't good enough, then on the other end of the spectrum, and some of the most fanciest things that we have today is a deep neural network, and we've probably all heard of this. If you want to learn what a deep neural network is, this is a great website. It's called playground.tensorflow.org, and it's this browser-based thing that looks pretty cool. So this is actually not regression, where you don't predict a value. It's classification, where you just want to say, is a certain data point blue or yellow? And here's two inputs, so basically it kind of looks like linear, so x1, x2. And if I run this against this data set or this problem, then it's really easy. It can, like after a few runs, like after 100 runs, it can predict basically with 100% accuracy if a dot is blue or yellow, depending on its x and y coordinates. So that's awesome. But if you look at something a little bit more complicated like this, and I let this run, this is the equivalent of a linear algorithm. It will never find the actual, like a good model. So the training test loss is like 0.5. It's 50%, it's guessing. So the way how deep neural networks work is they introduce what's called hidden layers and neurons. So the idea is you still have very simple algorithms, just a simple take x, take y, find a weight, and then give me an error rate. But what if we feed the output of the first stage of this into neurons in a second layer, and they take this and they divide the stuff with different weights, and then they feed into a next layer, and so on. You can basically build very sophisticated neural networks with like hundreds of layers and hundreds of neurons. So, but this is a simple one. I created two hidden layers, same input still. Let's see how this goes. And it does take a little bit of time, but now it already found it. So now we have a very, very low test loss, under 1%. Good job. And obviously this model, this neural network, would also work with the super simple problem. And here's another problem that we can also solve. Takes a little bit longer, and it's not quite perfect. And it probably will never become perfect, but it's good enough. So that's how neural networks work. Super simple single operations called neurons connected together, and by basically feeding back the output from an earlier stage to a later stage is how you get the end model. It's not quite good enough for this thing, by the way. So this is, if you want to go back home and play with this, see how many layers you need to solve this problem. So that's neural networks. We want to try that. The other thing we want to try is it's a thing called feature engineering. And that is if we know a little bit about our problem and a little bit about our input parameters, then we might actually do something with our input parameters. And if we go back to this problem, if we knew that every classification looked like this, then we could easily solve this if we just don't take the x and y, but we take the x squared and the y squared, and we make a perfect circle. And it doesn't take very long to train this and be perfect at all. So that's the other approach we could take. One is the add more hidden layers, add more neurons, or be smart about how we actually feed the input values into the neural network. And if we take these, for example, and then maybe there's another one, and we do have like 2, 3, 4 hidden layers, and we go back to this weird problem, maybe this will now become okay-ish. So we can already see that it's kind of morphing into something that works. Test loss is 25%, so it's better than 50% just guessing. I'll leave this up to you to go back to playground.tensorflow.org and play with this, and it's, I think this is quite cool. All right, so back to our notebook. So this is us. So let's try neural networks. So I'll just try a very simple neural network with 3 hidden layers, so 32 in the first layer, 8 neurons in the second layer, 2 neurons in the next layer. I'll run this, and it'll take a little bit longer. I think the output, though, is this will still only perform and give me an RMSE of, I think it was like 8 point something or 9. We can go back to this once it's done running. But it's still not great. And the reason it's not great is because we haven't done any feature engineering yet. So I've basically just taken all of my values, like the date, the time, the pickup, where pickup to, and I'm just feeding them in as numerical values. But they aren't really numerical, right? So day of week would be something nice, because if I just feed in the day, then, well, the 5th day of a week is not better than the first day of the week, and certainly not better by a factor of 5, but the model wouldn't know this. It just looks like numbers. So the first thing we do is let's look at the dates, and we as humans, we might know that like Mondays to Fridays are pretty busier than Saturdays and Sundays, so we would expect the trips to be shorter on the weekends versus the week. Actually, that's what I thought when I got here on Sunday, and then 9th Avenue was closed for a street fair. So let's do that. So let's take the day of the week and make that a category too. So instead of taking numerical values, let's make it categories and have categories from 1 to 7 for the days of the week. Same with the hour of the day. We have the exact pickup day, the exact pickup time. Probably doesn't matter if I get picked up at 9:35 or 9:37. So let's turn this into categories of 24 hours. And then we can do what's called a feature cross and basically say there is some correlation between the time of the day and the weekday. So we can have a feature cross between the hour of the day and the day of the week. The distance, we already saw like from the early plots that there is a correlation between the distance we took. We might not know the exact distance, but the super simple thing to calculate is the Euclidean distance, the as the crow flies. Super easy to calculate. Let's make that a feature as well. And then for the pickup and drop-off, we have these super accurate GPS coordinates. They're actually more accurate than I doubt. That they might not be correct. Like with all the skyscrapers, I doubt that they're actually correct as precise as they are. And if you get picked up on one city block and you go to a different city block, like within that block, the rate should be about the same. So one approach to do this would be to overlay the whole data set that we have, like the box that we created around New York, into a number of buckets. So have like 10 or 12 or 20 buckets across and 10, 20 rows. And then we have these buckets, these blocks of pickups and drop-offs. And I'm starting with a 10 by 10 grid, but I don't know, 12 by 12 might work better, 20 by 20 might work better. Let's see, let's make that a parameter and find out which one actually works best. And then the last thing to figure out is like, so now we've already figured out the grid, like 10 by 10, 20 by 20, that should be a parameter maybe more or less might work. But also the neural network. I've got no idea if I need 2, 3, 4, 5, 6, 8 hidden layers and how many neurons. And to figure out which one works best is what we do is we run a number of experiments. We just try different parameters, run them for a while, and then see which model gets us in the best direction. So which model gets us the best RMSE for, let's say, 5,000, 10,000 runs. That is called hyperparameter tuning. We basically take the same or similar model with different parameters, run them, wait for 10, 15, 20 minutes, see how good they are, and then we pick one of the models to run this. And then the final thing we want to do is like everything I've done so far is like 10,000, 100,000 records. We have 150 million records per year. So let's run this neural network against millions of data points just to get a better model. So I'm doing a lot of the stuff on the cloud, so I have to set some stuff up on my cloud and update my SDK. I've already done that. We're copying some data. And then this is basically how I do my feature engineering. So I say, here's my category, Sunday to Saturday. I still feed the numerical columns like the pickup long, pickup lat as it is, but then I also do my bucketing somewhere. Right, this is my buckets. I create buckets between 38 and 42 latitude, and then I just create as many buckets as I specify my parameters. Here's my feature cross between the day of the hour of the day and the day of the week. There's also a feature cross between the pickup location and the drop-off location, because that might teach the model something. Like, right, if I get picked up at JFK and I go to downtown, that's a good feature cross. So this is my new model. This looks a lot longer than what I've done before, and this is also what a serious data scientist would go through. They would actually want to be as good as they can in feeding the right values to the model and then doing some math magic before they actually train the model. So that's all that. Code. This is me training this thing locally. This will probably take a while. I'm only running 10 steps, so that's actually not that much. Running this for a bit, and you can already see this from my previous run. After I've trained this locally, it gave me I think it gave me an RMSE of 74, which just happens to be, or it gave me the square was 74, so then you take a square root of 74, 8.6, which is getting back to where I was, right, with my benchmark. So this is kind of telling me I'm going in the right direction. This deep neural network seems to work. If I can train this locally with only 10 iterations of a very small data set, I might be going in the right direction. So then the next thing I do is I want to run a lot more iterations. So instead of running 10 iterations, I want to run 5,000. And that's something that I don't want to do locally. By the way, when I say local, this whole Jupyter notebook runs on a VM in the cloud too, but it's just a single VM that has limited compute power. So now I run this against a machine learning service. So I run this against Google's machine learning engine, which is similar to what I think Oracle might release in the future, where I basically say, here's my model, I'll submit it to you guys, you let it run, and they spin up a cluster of machines and distribute it across the cluster. And if we look, this was a job I probably started yesterday. There's a new job. This is running now. This is the same job I started yesterday. It runs 9 minutes, and then after 9 minutes, you can actually have a look. You can look at the logs. And then I think one of the last outputs of the logs is again, not the square root, it's just the square of what we wanted to have. Let's see if we can find it. If you find it before me, let me know. Here it is. So 88.75. That's slightly less good than what I trained locally, but it's only a small data set. And it was also just a guess for the grid size and the neural network. So the next thing I did was, this is running in the background. The next thing I did was do the hyperbarometer tuning. I still don't know how many grids do I need and what kind of neural network do I need. So I basically said, let's try some stuff out. So we have the batch size, it's one of the other parameters, the number of buckets, et cetera, et cetera. We want to evaluate this by the RMSE, so please minimize that from us. I had to modify something here. This becomes our config. So I say, please try this and try the training batch size, which is some internal parameter between 64 and 512. Try the buckets between 10 and 20. And then only try these 3 categories for the shape of the neural network. I could have done more or less. So when you submit this, this will now run the same job that ran for 8 or 10 minutes. It will run 10 or 20 of those jobs. And this is where you definitely want to do the training on the cloud, because I don't want to wait 80 minutes or 90 minutes just for the output of this. So again, you run this on the cloud, they can run stuff in parallel and spin up resources as needed. And the output of that looks like this. So it will, in this case, it ran 10 trials, and it sorts them by the RMSE. It had a limited amount of steps, so the RMSE is still pretty bad. It's still at 9 point something. But what it tells me is that this shape, so the bucket size 10 actually worked well. So when they used 20, it didn't actually improve the RMSE by much. Actually got worse. Same with the training batch size. Bigger training batch sizes seem to work better. And then in terms of the neural network, this was the best that they could go up with. 128 neurons in the first hidden layer and then 32 in the second was the best of this output. So I ran this, and this job ran for start time, end time, 20-something minutes, so not even very long. And then I said, well, let's use this, obviously. Actually, I think when I first ran this, it had a different shape, so my actual run has something slightly different. So now I have that's running the hyperparameter job. That's what I just showed you. And then I can run this against data with the correct hyperparameters. So you see my shape was actually different. I had 4 hidden layers, and the first we had 64 neurons. So I ran this, and then the RMSE dropped to like $5, $6, $7, which was pretty good. And then I said, let's just run this with a lot of data. So I threw 2 million records on this, and I just kept increasing the number of training steps. So remember, the first one had 5,000, and this is now 1.6 million training steps. So that's quite a bit. This took quite a while. This overall, this ran for, I think, 14, 15, 16 hours until I stopped it. And it's not quite cheap. I think I ended up paying like $80 or $100 for this. So you don't want to do this every day, unless someone pays you to do this. But it was good fun to play with. And then I guess the last thing I want to show you is you can then run an application called TensorBoard, which is a web interface to TensorFlow, which shows you some metrics around. You can see how the RMSE improved with the number of training steps. You can also see when it might make sense to stop running this thing. This always takes like a minute or so to start up. I hope. Yeah, this looks like shit. This is what I wanted to actually show. This is the same thing from a previous run, and this does not look so great on this screen. Let's make this somewhat smaller. This is the the error. So we started out here, and the error was like 80 something. So that was kind of like a previous run. So we saw that after 5,000 iterations, was still at like an RMSE of 9. So 9 squared is 81. But then you can see as I kept increasing the training runs, 200,000 runs later, it was better, 73. So that's what, 8.5 or so. This must have been kind of where we surpassed the initial benchmark. With an RMSE of 8, that would be 64. Actually, we passed this here somewhere. And then you can see it kind of tapers off. So it doesn't get that much better the more compute resources you throw at it. So I'm still stuck at the RMSE of what? 20 something. That must be when it when it comes up with a model that really doesn't work very well. So it doesn't seem to be that stable. So it just says, let's try out this different weight for one of the functions. And it just happens to be bad. And this also happens when you look at, like, remember this thing? You don't filter it out? I didn't. But if you look at this, you also see some spikes here a little bit where you see the model just being, right? So now it's being unstable. And it just tries something, goes into one direction, then realizes, oops, this doesn't work. You kind of want to have this. Like, you kind of wanted to explore a little bit and find the minimum not right next to it, but somewhere outside of it. So you kind of want the model to, or the training job to explore and to go up the spike, because who knows, at the end of the spike, there might be a deeper valley. But if not, then you can always go back. So I think that's what these spikes are. And you can still see that you have this a little bit even in this model. So that's the same thing that we basically see with our model. But then obviously the other question too is, at the end of my training, am I at a local maximum or minimum? Am I where I want to be? Or should I just keep training this a little bit longer? But that's kind of where I left it at. So that was the end of the job. Here's an overview again of what we did. So the very first just rule of thumb, that gave us an RMSE of about 8, just by taking the Euclidean distance, and it was super cheap and fast and easy to run and understand, and every one of us could understand how we got to that number. Then we did the local training with linear regression, which gave us an RMSE of like 9 point something. So we were kind of disappointed by using machine learning, but it wasn't any better. Then we applied feature engineering and the neural network, and we were still not really improving, and really took us to do the hyperparameter tuning to figure out the ideal shape of our neural network and the grid size and the training batch size. That got us in the right direction, and then throwing lots of data at it and compute cost and letting it run got us to somewhere better. Also, like, knowing this, the question then is, how good would the linear regression be if we just were smart with the feature engineering, right? So that's the other question too. As I said, I spent $80 or $100 training this thing. Now it would make sense to go back and say, let's try our feature engineering on the local training, on the linear regression, try a simpler model again, now that we know how the data stuff works. I didn't do that. And then I wanted to use the model for prediction, and I have to cheat a little bit because the versions are incompatible. I can't run this in the notebook, but I can run this on the shell. Let's increase the screen size a little bit. If I can find how that works. Just any guesses? I stayed at a hotel, Central Park South to here. Like, what's your guess? Taxi fare? 50? 15. All right, so let's see what we see. So I've got a JSON file here. So this is like day of the week. Today is Tuesday, right? And I left at 9 something. Actually, I think it was 10. I tried 9 and 10. Didn't make a difference. This is my hotel address or the longitude latitude. This is here, Javits Center. Passengers were 2. I had my wife with me. Also didn't make much of a difference, right? The taxi fares, like I left this in as a feature, but I also know that the number of passengers should have little to no influence. I guess unless you fight and you ask the taxi driver to stop. All right, so I ran this, and then I'm running this local prediction. So this is actually running the prediction locally on like this machine or this shell. And it told me $10.50. So that's what I was expecting. And then I sat in the taxi and I was like, please let it be $10.50. And it ended up being $15.80. So 15 was pretty good. And then I went back to Google and said, so shit, why didn't this work? Obviously, I could have just been an outlier, but the day looked like normal data. It was not irregular traffic. And then I found that they increased the rates. Yes, sir? But with your error of 5, does that kind of always be plus minus? Kind of. I guess you could say, yeah, I guess you could say it's within the error range. But then the other thing too is, so all the training data is 10 years old, or it's like more than 2 years old. So back then, a mile was 40 cents, or a fifth of a mile was 40 cents, now it's 50 cents. So a 25% price increase, and then there's some additional minimums and surcharges. So I'm actually not that disappointed. I'm mostly disappointed that I didn't take this right last year and I didn't get closer to this. And also the problem now becomes, if I wanted to actually improve my algorithm, how would I do this? How would I muddle with the existing data from last year? And would I try to basically say, well, every rate should be 25% more, but it's not actually that accurate. So I was thinking about how would I actually improve my existing training. Well, the actual data has, so it has the trip distance. So from the trip distance, I could get the distance-based fare, and then I have the time. So I guess I could actually calculate the new price based on the rules. Yes?
It seems like the problem is the Euclidean distance is very inaccurate because the actual distance is a lot longer.
That's also true. But so the Euclidean distance, like in this case, I just use this as one of the input parameters to my training model. And it's one thing that's obviously super easy to calculate and cheap to calculate. Yes, I could also, like if I actually wanted to solve this problem, that's basically maybe also another good consensus, I guess or an outcome of this is, if I wanted to actually solve this problem, I would probably go to a routing engine, get the actual distance, get the traffic right now, and then get that out of there. Instead of just using machine learning on basically stale or dead data. But you're right, the Euclidean distance isn't great. And maybe I could try to teach it about where the bridges are and where one borough ends and the other starts. But that's a lot of work. Like to put that into a code and to put that into a model, that's a lot of work too.
Google Maps API.
Google Maps API would serve me that. But then that's an API call, and if I want to do like 1 million predictions, that's expensive in terms of money and time. Yes? Yep. Yep. No, I totally agree. And that's also, I guess, what the job of an actual data engineer or data scientist is not just using some of these things that the press says machine learning will take over the world. No, we still like having some human insights and having a human actually shape it a little bit and know when this works well versus when it does work so well, I think is still one of the very important things that we have with this. You also had a question.
Are you able to introduce like outside data into this model so that, like, for example, your time starting in time versus the flights landing taking off, and then also before Uber lift, after Uber lift?
Yep. So what I have done is I ran another lab that correlates it with weather data. So they joined weather data from one of the weather stations. And what I tried to do there was I tried to see how many taxis are on the street at any given time. And basically if I'm a taxi driver, what's the best time for me to be out to make money? And I thought weather might have something to do with it. So if it might be better to go on a rainy day because people are willing to pay more for shorter routes. You could also look at other certain days where people pay more tips. Other things would be if you have an event calendar of when do we have like events like the New York Marathon when all the roads are blocked. That might have an influence. And yes, that's other things that you might also want to do is see which other data you can join to this to get some more insight. Yes? Yeah.
I was wondering if there are any automated frameworks that you use in order to, fluctuate the
So I used a little bit of the Google magic that they have. What I did is I gave them basically the boundaries of what I wanted it to experiment with. And then when I submitted the hyperparameter tuning job to the AI platform or the machine learning engine, it kind of knows it doesn't run all of my 10 or 20 runs in parallel. It runs 2 or 3 in parallel only. And then it sees this one thing worked really well. So then it tries to also look into that direction. So it does some optimization. I didn't look too much into how it actually optimizes this. All right. Yes?
So is your usual flow of as a data scientist using these basic, more simpler GPU models like you put in
Yeah, yeah. So the question is like, do you use the simpler models? I would say yes, because the simpler models are usually available in these database engines themselves. So I also don't have to worry about where do I train this, where do I run this. If I want to make this a service, now I have to have an API. So if you can run it directly in the database and then run it from PL SQL or just as a SQL function, that's super easy as well. And you have all the data there, so you don't have to move it around. And I guess that's the other thing. So I'm not a data scientist. I'm mostly a data engineer. I work on building data warehouses, but I wanted to understand what people doing machine learning actually do. So this is why I started this exploration. And I don't understand most of the algorithms. I understand linear regression. I kind of understand neural networks at the level that I explained it today. But I know there's like 100 different other algorithms and models out there that some of them I think I know what they do. But again, that's where people also bring value, because they might know this is a problem that works better with a decision tree or with a random forest, or now I'm just making up words that I think exist. So that's, I guess it's the other magic that an actual person who knows what they're doing bring with a strong mathematical statistics background. They actually know which algorithms might work best. And then you find like that what we do in our job, Pythian has a data science practice, and we find that sometimes you can do a lot of good insight with just something like a linear model or a simple decision tree that doesn't have to be super fancy. It doesn't have to be a neural network. We have several clients where the biggest, or the things that have the biggest impact are super simple algorithms, but they solve good problems for them. And then you spend, like I said, you spend $100 trying to, I spent more money. I could have taken 10 taxi rides for the amount of money it took me to incorrectly predict today's ride. Right, so that's the other aspect of that, yes.
So there's one more item like this. This is the mandated price, let's say, from here to JFK is
Mm-hmm.
the city specifies 7 things. Those factors are not included, right? Like probably.
Correct. So, and again, if I had to write an algorithm, I think what I would try to do is, like, for example, I would try to be smart and I would take out the flat rate, because I know that if my pickup point is JFK or like a certain GPS coordinates around there, and my drop-off is Manhattan, I know what the rate is. So if I had to write this thing as an API, I would probably say, if it's one of these special cases, then take that out. But then that also means that all my training becomes more complicated, because then I also need to take out these data points out of my training, and it might make my model better. And I could do the same thing with the other, like there's the late night surcharge and the day traffic surcharge. I guess if I really wanted to get the best model, I would probably want to code all of these rules in there and help. And for example, these surcharges, I might just have a constructed feature that just says in rush hour, not in rush hour. And then that's a binary feature, and it really helps the algorithm.
Partition the data, for example, different geography.
Yep.
Manhattan versus that.
Yeah. Yes, one more question.
Which first is depth of the neural net? How do you decide that? How wide do they trial and error?
Yeah, in this case, I just tried this out. I just said, try 3 or 4 different shapes, and then I did the hyperparameter tuning. It tried different ones, and it said this one is better than the other. But yeah, mostly I had no idea. What you can do is, there's this TensorBoard. There's a lot of different graphs here, and I think some of them, if you know what you're doing, help you make these decisions a little bit better. Because what you can look at, for example, is you can look at the individual contribution of the neurons. And if you see, for example, there's a lot of neurons not actually doing much or not contributing much to the end result, you might make your neural network smaller. So that's something that helps. So there are ways to do this with like looking into the actual TensorFlow training job. But in my case, I just took a guess, and then I said, let's try 3, 4, 5 different shapes and see which one happens to be okay. We're running out of time, but I'll take this one more question.
I was just wondering if there's such a thing as like meta machine learning, which so there are ways that there are like there's machine learning that would recommend parameters that you use. Like
Yes.
These are the parameters that you should try. This is the network.
Yes, and that's all the rage now, is these companies trying to make the frameworks easier to use. So now the cloud vendors are actually introducing frameworks where you just upload your data set and you say, this is what I want to train on, and they will automatically, they basically did all the experiments that I've done and just recommend this looks like a linear regression and this is what your parameters should look like. It actually helps you out. So that does exist, and that's, I guess, the next frontier, is to make this stuff easier and more accessible to just random humans.
Something that's like open source that you can just play around with?
Well, TensorFlow is open source, so you can use that.
That will recommend things like that for you?
No, not by itself. I know if Keras is it's another abstraction on top of that. That might have something, but I think there's a lot of secret sauce that I think people are trying to hide. So I've seen this from cloud vendors. I've not seen that specific functionality in an open source tool. I think we're running out of time. I'm super happy to take more questions outside the room, but I think I should just be nice to the next speaker and get off the stage. Thank you guys for coming.